At the subatomic level, atoms strive for stability. When an unstable atom breaks apart, it ejects excess mass and energy into the space around it. That transfer of energy, moving through space or matter, is radiation. We are constantly surrounded by it, from the heat of a coffee cup to the light of the sun. This diagram shows the electromagnetic spectrum. As we move up into higher frequencies, the physics change. The energy reaches a threshold where it becomes ionizing. At this point, the waves possess enough force to violently strip electrons away from stable atoms. When those atoms are part of human tissue, ionization destroys a cell's ability to reproduce. It breaks the DNA chains, leading directly to cellular mutation and cell death. This specific hazard is universally recognized across industrial environments. That red and yellow trefoil indicates an environment where ionization is an active threat. Managing this threat falls to the safety professional. Their job is to translate these physical subatomic events into measurable biological impacts on the human body. Protecting workers from radiation requires a deterministic, mathematically precise engineering approach. Safety professionals build their understanding from the atomic scale up to the facility blueprint to create a complete safety model. The mechanics of this hazard begin with radioactive decay. This is the process by which unstable materials spontaneously emit particles or energy to achieve a stable state. This diagram compares two primary categories of emission. On the left, particle radiation, alpha and beta particles, involves the ejection of physical mass from the nucleus. On the right, electromagnetic radiation, gamma and X-rays, emits pure energy waves without physical mass. Because physical particles behave differently than pure energy, these emission types require different control strategies. Their ability to penetrate matter dictates how we protect against them. To control the source, we first have to know how long it remains hazardous. We measure this decay process using a predictable timer known as half-life. This chart plots radioactive decay. Half-life is the time required for 50% of the atoms to decay. We calculate future activity using the exponential decay equation shown here. The lambda symbol is the decay constant, calculated by dividing 0.693 by the half-life. Safety professionals use this formula because occupational safety standards require strict compliance. They must accurately predict the exact strength of a radioactive source months or even years into the future. Knowing exactly what type of radiation is emitting and exactly how fast the source is decaying is the absolute prerequisite for calculating human exposure. Tracking an invisible hazard requires tracing the energy from its point of origin all the way to the worker. This flowchart maps radiation measurement units. Step 1, activity, measures source decay in Curies. Step 2, exposure, measures airborne energy in Roentgens. Step 3, absorbed dose, measures energy deposited into materials in rats. Step 4, dose equivalent, calculates actual biological damage in REMS. Confusing the activity of the source with the biological damage is a common professional error. A Curie describes the machine's behavior. A REM describes the worker's biological impact. Accumulating dose equivalent leads to distinct biological consequences. Intense, immediate doses cause acute somatic effects, while lower, chronic exposures lead to delayed effects like cancer. Tissue sensitivity varies across the body. Rapidly dividing cells are highly vulnerable to ionizing damage, whereas the central nervous system is highly resistant. We understand these biological thresholds today because of early, unshielded industrial environments, where these exposure risks were first documented. Correctly translating physical Curies into biological REMS is the only way to establish the target limits necessary for designing physical engineering controls. To keep dose equivalents below permissible exposure limits, safety professionals rely on 3 primary engineering controls: time, distance, and shielding. Time is a strictly linear control. Cutting a worker's exposure time in half reduces their accumulated biological dose by exactly 50%. Distance is the single most effective control vector. This is dictated entirely by the physical geometry of expanding energy. This diagram illustrates the inverse square law. As radiation expands outward, doubling the distance from the source quadruples the area it covers, dropping exposure intensity to 25%. Engineers calculate safe perimeters using this specific formula. This principle dictates physical handling tools. By maximizing space between the worker and the isotope, they mechanically enforce the inverse square law. However, when operational tasks prevent workers from maintaining adequate distance, facilities must implement shielding. Effective shielding relies on the attenuation coefficient, a metric that characterizes exactly how easily a specific material can be penetrated by radiation. This visualization shows the half-value layer, the precise thickness of a material required to cut the dose rate by 50%. With each successive layer, radiation drops by half. It's calculated by dividing 0.693 by the material's attenuation coefficient. These calculations dictate the manufacturing of personal protective equipment. A lead apron is a direct, wearable manifestation of calculated half-value layer shielding. Achieving OSHA compliance requires mathematically balancing these three factors. Time, distance, and half-value layer shielding must be optimized against the calculated REM dose to ensure total worker safety. Ionizing radiation is only part of the hazard profile. We also have to address the lower energy half of the electromagnetic spectrum. This diagram maps non-ionizing radiation. This includes ultraviolet, visible light, infrared, microwaves, radio frequencies, and extremely low frequencies. These energy waves lack the power to strip electrons from atoms. In this lower energy range, the primary occupational hazards shift from cellular mutation to thermal heating and deep tissue dielectric effects. Massive industrial sources, like these telecommunication antenna arrays, expose workers to intense radio frequencies and microwaves. Other processes create concentrated sources of visible and infrared non-ionizing radiation, requiring strict optical protection. Radio frequencies and microwaves present a unique spatial complexity. Their electromagnetic field behavior changes drastically depending on how far you are from the antenna. This diagram categorizes those behaviors into three boundary regions: near field, transition zone, and far field. Safety professionals must accurately demarcate these zones because control strategies and metering equipment depend entirely on which region the worker is in. Managing the thermal properties and complex field boundaries of non-ionizing radiation requires the same level of mathematical rigor used for subatomic ionization. All of these abstract formulas and decay constants ultimately result in the primary output of the safety professional, the engineered facility. The inverse square law dictates the exact placement of the physical barrier perimeters. The half-value layer calculations dictate the specific thickness of the concrete and lead walls drafted on the print. This combination of math ensures the facility operates within the strict legal boundaries of OSHA Standard 29 CFR 1910.1096. Ultimately, effective radiation safety relies on mastering physical mathematics to engineer a perfectly controlled environment for human biology.